We are going to solve an example of finding eigenvalues and eigenvectors. The Hamiltonian, like I mentioned in the class, is the total of your mechanical energy, is written as omega sigma z. Sigma z here is called a Pauli matrix in X in Z. Omega here is a constant, so usually it's an angular frequency. So your sigma z here is given by a matrix 2 by 2, 1, 0, 0, minus 1. It's a very nice 2 by 2 matrix. So therefore, if you substitute in H here, then it becomes omega 1, 0, 0, minus 1. So it's become omega 0, 0, minus omega. So you have a constant inside your matrix. So we try to solve the eigenvalue equation, or we look at transformations. Is H, so you have V, and then you have EV. So in class HV, maybe I put it like a matrix form. I can put it, should be MV lambda V. It's very similar. Okay. So using the finding characteristic equation, so we have characteristic equation. So you have finding determinant of H minus EI. So this is 2 by 2 identity matrix equals to 0. Then we proceed. So you have omega 0, 0, minus omega minus E 0, 0, E, and then equals to V equals to 0. So what do you do here? Finding determinants E minus E 0, 0, minus omega minus E. All right. And then equals to 0. Okay. You have to make it first like that. Finding determinants, okay? Finding determinant first. And then, so determinant of A, B, C, D is AD minus BC. All right, so let me put this, okay? You can follow the tips in my notes. So therefore, omega minus E minus omega minus E, make it equals to 0. Then this is you solve with omega 1 is omega, E1, and E2 is minus omega. So you have 2 eigenvalues. Then we substitute for E1 omega, H omega I. This is we try to find V1 equals to 0. Then you have 0, 0, 0 minus 2 omega. Then this is your x1, y1 equals to 0. For these sides, your y1 definitely 0 because 2 omega y1 equals to 0. So this definitely this. Therefore, your x1 is arbitrary. Then your v1 vector is, you choose 1, 0. This is like your x1, y1. So for E2 minus omega, similarly, okay, so you have h plus omega I V2 equals to 0. Then you have 2 omega 0, 0 x2 y2, so this is 0, 0. Again over here, your 2 omega x2 equals to 0, so this implies x2 equals to 0. Then your u2 is arbitrary. Therefore, your v2 is 0, 1. We choose 1. So if you want to diagonalize, so your C here is actually 1, 0, 0, 1. So determinant C is definitely 1. It's a rotation, positive rotation. Okay, that's how we did it. So if you have minus 1, definitely similarly 0. Okay, so you have C1 HC, so this is a diagonal, omega. Zero, 0 minus omega. So this is a diagonal matrix. Let's say your V1, you want to norm, finding the norm. So you have V1 like that, 1 over square root 1 square plus 0 square, and then 1, 0. Similarly for V2. Okay, done.